So this is a very ambitious title. I realized that fully when I tried actually preparing the talk. So I've made some a slight change. It's going to my current understanding, and it's not really being only understanding. It's also going to be questions. And of course, it reflects collaborations with many people on cruises and in the lab, so I won't cite them. The talk is organized in one main part where I've tried, because the understanding you have of a topic, of course, is built on history of science also, especially for somebody who's been working on the same topic for many years like me. So I've tried, and since it was kind of an anniversary colloquium, I thought it was good to start from the beginning. And so I'm going to talk about the three ingredients, really, of plate divergence at Mid-Oceanic ridges, which are magmatism, tectonics, and hydrothermalism. Discoveries, evolving concepts, new and old questions, and of course it won't by any means be overarching or anything. I'm going to leave a lot of things out because it's only 24 slides. And then I will finish with a few suggestions for perspective for future Mid-Oceanic research. So starting from the beginning is the Hess diagram, that conceptual sketch that we saw yesterday. And as it was pointed out yesterday, this initial sketch really doesn't really create plates. It has the convective flow of the mantle coming right through to the surface, and forms the oceanic crust by hydration of the mantle material. The thing that is very striking is that it also has the water coming from underneath, from the mantle, not from the ocean. And so that's the start in 1962. And then this is a busy slide, but it's discovery of the magmatism ingredient. And it starts with, of course, it's based on many cruises, heat flow, gravity, seismic, magnetics, and of course also sampling cruises. And the sampling cruises show that the Mid-Oceanic ridges are volcanic chains. And then there is the modeling and the understanding and experimental work on peridotites also that allowed people to build the first models of mantle melting. And I'm just adding, because I'm not going, it's one of the parts I'll skip, and that's clearly a very big important part of my understanding of ridges, is the ridge melting models that were mostly elaborated in the 80s and 90s. That allowed predicting parent morb composition. And where is it? Okay. And the crustal thickness as a function of mantle composition and temperature. Mackenzie, Groove, Bob White, and Charlie Langmuir. And so the third part is that the oceanic crust is made of basaltic rocks, and that's really the outcome of a field conference that took place in 1972, and that brought together people working on the oceanic crust and people working on the ophiolites, and came up with this very famous layered crustal model with the crust made of different types of magmatic rocks. Then starting a little bit later, and really starting with the famous years, the famous experiment that Xavier Le Pichon told us about yesterday, it's the discovery of really the role of tectonics, and particularly, as we will see, at slow-spreading ridges. So the famous experiments were a very impressive exploration of the mid-Atlantic ridge, and it discovered that this ridge has an actual valley, and that this actual valley is produced by tectonic extension. And I put big letters here because it's a very fundamental discovery that was really made in a paper by Taponi and Franchetot in 1978, that the lithosphere is not zero thickness at the ridge axis. And being of a finite thickness, this rigid plate could be deformed, and that was how they could explain the actual valley. Models of deformation of the actual plates now are different, but that was the basic idea that you had to take into account the existence of an interplate domain of lithosphere. And then there is the third ingredient, the hydrothermalism. And hydrothermalism was first predicted on the basis of heat flow data. I put here the conceptual model of Lister in 1972, but there were lots of heat flow cruises that pointed to that direction and showed basically that the heat flow at the ridge axis was too low, and therefore a lot of heat had to be expelled by some convective mechanism. And this is a cartoon that was made by Lister showing it's in a cross-axis sketch. This is the ridge axis, and you see how he sketched the necessity for hydrothermal cells. And here it's what happens to these hydrothermal cells if the ridge is set, if you go far away and you have sediments. And so that was in 1972, and then the actual vents on the Galapagos Ridge were discovered later in this 1970s. And these are places where actually the vents were not really directly observed, but they were measured by temperature measurements. And then later on, they were actually discovered in 1979. And what's really, of course, of primary importance is that they also discovered that vents were a place for a very specific type of life. And therefore, aside from being merely a way of expelling heat, hydrothermalism is also the place where you can feed chemiosynthetic life and also a lot of transfers from the solid earth to the ocean. So these are the ingredients. Now I'm going to go to a very important discovery that was made a little bit later on, which started with a discovery of the actual valley and the comparison between the actual valley and the actual high at fast and intermediate spreading rate ridges. And this is a sketch from 1982. And a little bit later on, kind of based on this strange discovery of a systematic inversion of the topography associated with Mid-Oceanic ridges between slow and fast-spreading ridges, there were various types of geophysical experiments. And here I'm showing the most important result for fast was the discovery that you have just less than 2 kilometers below the seafloor, just on axis here. This is a cross-axis profile. You have systematically a reflector that's interpreted as the top of an actual magma chamber. And we know now that it's not a fully magmatic place, but it's a melt-mush zone with a melt-rich lens at its top. And this melt-rich lens appears to be a permanent feature of fast-spreading ridges. And this is, of course, a very important constraint. And then at slow-spreading ridges, I think a very important geophysical constraint concerns actually the thickness of this lithosphere that is deformed to produce the actual valley. And it was a paper by Toomey et al. In 1985 that relocated earthquakes measured with OBSs at the mid-Atlantic ridge and found that the maximum depth of these earthquakes was 8 kilometers below seafloor, showing that you had a seismogenic layer on axis of at least that thickness. And then there was the first thermomechanical model, or the first generations of thermomechanical models in the early 90s that focused on trying to put some kind of modeling behind these observations here. And what they did was a thermal model as a function of the spreading rate. And what it shows you is the predicted isotherms. And it's compared with the actual data that they had at that time, which was actually this one here, telling them that at the half spreading rate of the Mid-Atlantic ridge here, you had to have a seismogenic lithosphere at least 8 kilometers deep. So that's this case. And then the fact that you had a permanent actual length at less than 2 kilometers told you that you could have you had to produce a model that would locate your isotherms here. And this model, of course, used completely ad hoc hydrothermal cooling, and one big result was to tell us that hydrothermal cooling had to account to most of the heat lost by the ridge system. So conductive heat loss was negligible compared to hydrothermal cooling. And then, well, that's actually, I've put this very old-looking diagram because I think it conveys the idea that it's the consequence of having this thick lithosphere layer that allows to explain why it's very frequent at slow-spreading ridges that you find outcrops of serpentinized peridotites and gabbros at the seafloor. And so the idea was that in order to find these rocks that are formed at depth at the seafloor, you had to have big faults, big normal faults crossing the actual lithosphere, and that you actually had a process by which these rocks were formed in the asthenosphere and interacted with melts all the way up to the seafloor. So here you would have, this is expressed here you would have interaction between hot mantle and melts. Then here, these rocks would be uplifted and would be allowed to be intruded by a little bit more evolved gabbros, and then you would have, etc. And all of this was based on studies, petrological studies of rocks actually collected at the seafloor. And more recently, and I'm showing you the very most recent set of data to constrain this idea, was that these faults that exhume mantle-derived ultramafic rocks and gabbros at slow ridges are actually convex downward detachments with a lot of footwall rotation. And this shows you the results of a recent microseismicity study experiment at what we call now a core complex area at the Mid-Atlantic Ridge at 13 degrees north. And notice, by the way, I'll come back to that later, that now that we have OBSs that are able to record and relocate much smaller magnitude earthquakes, we see that this limit is actually going down a little bit. So the maximum depth of earthquakes at this ridge is actually about 12 kilometers here. And this is the kind of conceptual sketch that corresponds to this situation, in which you have the ridge axis here with concomitant volcanism, and then the footwall of this fault that is exhumed and rotated, and you have a little bit of compressive deformation here that accompanies this rotation. So another thing that was discovered quite interestingly is that this ultramafic seafloor, the result of the activity of these detachment faults, it can actually be estimated through several means to represent about 25% of the seafloor that is accreted at slow rates, so less than 40 millimeters per year. And these are the darker gray areas in this map. And I think it's really interesting to see that very often it has been said that serpentinized peridotites originated at slow-spreading ridges could contribute to the water budget of subduction zones. And I think the talk by Cesar Ranero just before showed us that actually a lot of the serpentinization that carries water down the subduction doesn't come from the ridges, it comes from the subduction itself. And you can see that very readily here because actually plates that are subducted at very major subductions, they have been formed, the oceanic plate has been formed at a fast spreading rate, and it makes a lot of sense because subductions are a very big pull on the plates. So now, just something about fast ridges. Again, I'm not going to be comprehensive, I'm not going to cover everything, but that's something very intriguing about fast ridges is that we have a pretty good understanding that the crust is magmatic, but we actually know very little about how the lower crust, so the crust below the dikes and the lava flows, actually crystallizes. And there are still two unmembers models that were produced by authors in the 90s. One is that everything crystallizes in these actual melt lands here, with the heat readily evacuated by the hydrothermal systems here, and then the crystals just fall down, and this is in a cross-axis section. And then the other model that was built by Kelman and others, based on actual petrology of samples from the gabbros in the omanophyolite and the comparison with oman and actual fast-spread oceanic crust may be a discussion, was more in favor of having a crust that is built progressively by magma crystallizing as it goes up to the dikes and to the eruption sites. And the big problem in this one is how do you extract the latent heat of crystallization from deep into the thing? And so even models that have been developed by petrological studies of the few samples of gabbros from fast-spreading ridges, they tend to favor B or A plus B, but there is really this question of how you get the heat out. And I'm just showing here something that I think could be related. And it's the idea that these models of crustal cooling that we've seen, they are cross-axis models. But actually, when you look at the actor of the cooling, the hydrothermal system, it operates along axis, and that's really clear. First of all, all the vents are in this narrow zone that is called the actual summit trough, and where most of the eruptions are documented to occur. So most of the melt comes up beneath the ridge within this 500 meters about region of volcanism. And then when we look at the earthquakes that can be associated with thermal cracking at the base of the downgoing slabs, downgoing hydrothermal plumes, they're all along axis also. So there is absolutely no hint of an active cross-axis hydrothermal system. And another thing that is very clear from both observation, modeling, geophysical seismic imaging of the melt in the meltlands and underneath, is that there is a strong coupling between this along-axis hydrothermal system and the melt system underneath. So just as a kind of a provocative idea, we tried with Fabrice Fontaine and Michel Rabinowitz to just look at what would be the conditions necessary to couple not a cross-axis convection in the gabbroic crust, but a long-axis convection in the gabbroic crust that would allow upwellings of melt to be coupled with the distribution of the vents. And this is really based on this very well-studied part of the East Pacific Rise, where you have the most recent lava flows in green, and in yellow you have the actual vents. And these squares are various types of actual discontinuities that were documented by Suzanne Carbot et al. And what it shows is that for certain type of conditions, it's possible to actually extract the heat by a long-axis convection of the gabbroic mush. Now the question is, are these conditions realistic in terms of actual rock and petrology? And so that's more like an idea for future studies. Continuing on hydrothermal systems, and that concerns all the ridge hydrothermal systems, fast and slow. The problem is that we've seen that the hydrothermal fluxes are important for life. Obviously, and I'm going to show you a slide about that, they're also important for what type of chemicals are transferred from the solid earth to the ocean. They are important for heat transfer, but their fluxes are at present very poorly constrained, and one of the main reasons why they are poorly constrained is that they are partitioned into between focused that represents a smaller part of the flux, and diffuse vents. And the diffuse vents, here is the cartoon showing a full upflow zone, hydrothermal upflow zone with the actual magma. And here at the vent sites, so that would be 1 kilometer about a hydrothermal field. And here you have one vent site, and you have several smokers, but you also have diffuse flows, and you have lots of evidence of secondary circulations with seawater. Incidentally, that's where the life is. So if we want to understand the life at hydrothermal vents, we need to understand this. We don't really know, and you can see even at a very well-studied place like the 950 North EPR smoker vents, the current estimates of the fluxes are okay for the smokers. You can count the smokers and estimate the flux, but they're very, very poor for the diffuse, and the diffuse is about 1 order of magnitude larger. So it's very important to try to understand this functioning at the vent site scale, and that's, for example, what is being done at observatories. There is one at the Mid-Atlantic Ridge. It's called the Azores European Observatory. There are also some at the Rendezvous ridges to monitor primary and secondary hydrothermal circulations and their impact on life and heat plus chemical transfers to the ocean. And that's an example of a temperature sensor in a smoker. About chemistry, that again concerns fast and slow. You have a diversity of end-member hydrothermal fluids. So if you want to estimate the fluxes to the ocean, you have this diversity, plus all the transformations that certainly do occur to diffuse fluids due to life and also to reactions during the mixing with seawater in the subsurface. And so I've shown you here a summary of temperatures, pH, and composition of 3 types of vents. One can be found at both fast and slow. It's basalt roasted and it's magma fueled. Then the 2 others are found only in these 25% of the places where you have fluidities at the seafloor. And some have black smokers and they are magma fueled. It means that you have an ultramafic seafloor, but you also have a gabbro pocket underneath that is cooling. And the other one is not magma fueled, and it's lower temperature compared to the others. It's also much higher pH. What characterizes the sites that are on ultramafic seafloor is that they have much higher hydrogen and methane, okay, because these are byproducts of the serpentinization reaction. And one thing that characterizes the sites that are magma fueled is that they vent a lot of metal-derived CO2. And then there are large differences in the amount of iron, with no iron at all for this last one. Okay, so obviously we need to learn more about the distribution and relative importance of all of these things. There is also, in the case of the last one, the one that is non-magma fueled and ultramafic hosted, the discovery that the venting is actually very low flux, low heat flux, low volume. This is an example of carbonate constructions that are produced by fluid that is oozing out of cracks in the ultramafic seafloor. And what happens, we think, and this has been observed at several places, is that it's the mere fact that this fluid is high pH that allows it to react with the seawater and precipitate, in this case, a carbonate and here a brucite, from ingredients that are actually, for the most part, contained into the seawater. So that's obviously, and the spatial distribution of these vents is very unknown. So I'm going back to tectonics now for the end of the talk. Going back to ultra-slow spreading ridges. And here you have the Mid-Atlantic Ridge passive seismic experiment results that I showed before, and we'd seen that compared to the early 90s thermal model, the lithosphere was a bit thicker than predicted by this model. We now look at earthquakes occurring at the Southwest Indian Ridge, and we see that we have a volcano, and then as we move away from the volcano, the maximum depth of the earthquakes that are relocated can go down to 25 kilometers below seafloor. And this is where it should be in terms of spreading rate, and I can't even fit it on the slide. So there is a very big problem of understanding the thermal regime of parts of the ultra-slow spreading ridges, and it's really an open question for the future. One way of tackling this problem is to relate these areas to the actual geology. So this is the actual the volcano that is imaged here. And this is a kind of a structural / geological map that is done over a several hundred kilometers area that shows you several types of seafloor, and mostly this one where all these faults are sketched, where dredging shows that we have a nearly amagmatic spreading with emplacement of peridotites on both plates for the past 11 million years. And this corridor of nearly amagmatic spreading is located between these two actual volcanoes. And this is the sketch we did from the distribution of these faults here, and from the fact that we have we can document symmetrical spreading on both plates, even in this corridor, and so what it leads us to is to propose that we actually have a system of detachment faults as represented at the Mid-Atlantic Ridge, but these detachment faults, they flip polarity. So it exhumes on one side, and then a new fault is initiated and it exhumes on the other side. And you get to this system. And if we take a look at the actual valley in this context, so that's a view from the west. We have images that it looks like a landscape, but it's actually seafloor reflectivity. And we can see that all the gray parts is the ultramafic seafloor. This is documented by dredging and also submersible observations. And here we have volcanic ridges that are built directly on top of this ultramafic seafloor. And so this entire area probably is very, very thick lithosphere. So this is what we call the Melpour Eastern Swears Field Laboratory, where active tectonics, hydrothermal, and sparse volcanic processes can be studied at the melt-star divergent plate boundary. And you notice that I use divergent plate boundary and not Mid-Oceanic Ridge, because what I'm aiming at is that there is actually a lot of not really analogies, but more like reasons or good comparisons to be made between this type of environment and the distal parts of divergent continental margins where exhumed matter has been documented. So that would be the first, and I numbered it 3 because it's actually something that is ongoing, and I think it's probably a bit less ambitious than the other 2 objectives that I'm going to describe after. So the idea would be to develop comparative approaches, and that would be to mutual benefit with distal divergent continental margins, and also the initial oceanic crust that is formed here. The idea is that we can, using data that is mostly seismic data, but also sedimentary data that allows you to monitor subsidence and therefore have an indirect constraint on the thermal regime, study the effect of variable melt supply, sediment thickness, mantle inheritance on tectonic magmatic hydrothermal interplays, etc. And here I say mantle inheritance because at margins people are very used to think in terms of the inheritance of the subcontinental mantle and even of the different types of subcontinental mantles that you have, for example, beneath Africa, you have cratons, you have Paleozoic belts, etc. And it's something that would be really interesting is to extend this study of inheritance to first the oldest oceanic crusts created at these margins, and then ultimately, and I think this is really something that needs to be done, as was mentioned yesterday, is look at the old mantle under the young seafloor, okay? Because so far, I think we've looked at the effect of mantle heterogeneity on ridges, mostly from the point of view of defining geochemical provinces and not looking enough into geodynamics. And that has made it difficult for people like me who do mostly structural geology and things like that to relate the two. Okay, I know that we have the Dupol anomaly here. I also noticed that we have a huge geoid high. I noticed that the place I'm mostly interested in, which is this one, the amagmatic zone, which, by the way, is consistent with being very deep and having a very high sodium content basalts, that this zone corresponds to the edge of this province. But what is it exactly? Is it due to some kind of mantle inheritance inherited from the opening of the ridge? Or is it an active plume, etc.? We need to replace, what I think is that we need to replace the ridges in order to use them as tools also to better understand what's underneath. We need to try to replace them in the inheritance of the mantle underneath. And also to replace them in the inheritance of past plate tectonic cycles and look to plate tectonic histories. We haven't talked about that much in this conference, but I think it's really important to take that into account. And finally, I will leave that, and that's more ridge-focused, if you want. The first one would be to open up studies of ridges, to study the ridges as part of a more global system that does include the life and the ocean, and that concerns everything about the transfers of matter and the reactions and the carbonation, etc., etc. And then the other one is an opportunity that is made possible, I think, by technological advances in underwater monitoring techniques, is that, for example, faults and detachment faults and the associated seismicity may be really interesting to understand the seismic generation, the earthquake generation, and it's now possible to decide that we can use one of these detachment faults as a natural laboratory, because it's not such a big investment of time anymore, because the previous generation has put a lot of efforts to set a system of OBSs, of temperature probes in the vents, etc., etc. And so the faulting and seismicity is an obvious example of volcanism, but also, of course, fluid rock-life interactions. So I'll leave that here.